The foundation of data analysis is describing data with mathematical models. You can think of a mathematical model as a machine or nature that generates patterns of random data values. The machine or nature has control knobs that determine details of the pattern of data. And these control knobs are called parameters. And the knob's position is called the value of the parameter. So here we have two images. On the left-hand side, there's three knobs. So you could think of this as three parameters. And each position of a knob is the certain value of that parameter. So this, for example, could be related to a certain mix of music where you would tweak the lower end and the higher end and so on. And on the right-hand side, we have a shower head, where the shower comes out of the shower head to a certain location. So that location would be the first parameter. And the spread of the water would be the second parameter. So two parameters here, the location of the water, which you can change, and the spread of the water, which you can change, at least typically. So let's incorporate a little mathematical notation. The model is f of x given theta, a joint distribution of observable random variables x given theta. F can be, for example, the normal distribution indexed by theta. Such is the case with the app we are using. X is a random vector, so data, something observable. Theta is an unobservable parameter of distribution f. For example, theta is a vector of mu and sigma for the normal distribution. And we also possibly have a function g of theta, which is a joint distribution for the unknown parameters. In this case, theta would be considered random. So in this case, we are dealing with Bayesian statistics. Here's a way you can think about statistical modeling. First, you have your machine or nature that generates data through some process unknown to you. The data being produced or generated by nature is assumed to be captured perfectly by a function f. So this is a heavy assumption, but this is typically assumed that there is a ground truth model f that perfectly captures the data being generated by nature. For frequentists, parameters are unknown but considered fixed. Whereas for Bayesians, parameters are also unknown, but Bayesians consider them random. So in this case, Bayesians consider theta as random. So Bayesians incorporate also a prior distribution for the parameters, denoted here as G. Now, when you have a model, from that you can generate data. And the process by which this is done is called probability theory. For example, if you have a normal distribution with some fixed parameters, then from that you can calculate certain probabilities through probability theory. Now in practice, you don't know the ground truth model F. It's unknown to you, and it will always remain unknown to you. But in practice, the best you can do is get an approximation, F tilde. So this is in fact what we are dealing with in practice. So there is some bias between these two guys here, and how large it is depends on the situation. Now in practice also, what you observe is data. And from the data, you should somehow infer that what your underlying model is. And the process by which this is done is called statistical theory. So this is one way of thinking about statistical modeling. Bayesians refer to f of x as the conditional distribution of the observations given that the parameter equals theta. And frequentists refer to f of x as the distribution of the observations when theta is the true value of the parameter. So Bayesians consider theta as a random variable and assign a probability distribution to it. And frequentists consider theta as fixed and unknown. They assume that this theta, which is unknown, is the true value, whereas Bayesians consider theta as random. So this f of x given theta is therefore the conditional distribution of x given that the parameter equals some value of theta, which is defined by or it's affected by the probability distribution of theta. So these f of x, these data generating functions f of x given theta, they look the same, but they are not the same thing for Bayesians and frequentists. Let's take a decision theoretical approach for comparing the Bayesian and the frequentist approaches. This slide is heavily inspired by Professor Michael I. Jordan and his talk found freely online. And a link to that talk is found in the video description, and I highly recommend that talk to everyone. So first we define a family of probability models indexed by theta. Then we define a procedure, delta x, that operates on the data to produce a decision of some sort. Our delta x could be, for example, linear regression, support vector machines, decision trees, and so on. And our procedure produces some sort of decision, for example, an estimate of theta. Then we define a loss function. And we want our loss function tells us basically how bad we feel when our procedure delta of x deviates from the true value of theta. So we want our loss function to get as small values as possible. And then the goal is to use the loss function to compare different procedures, delta 1, delta 2, delta 3, and so on. So linear regression, support vector machines, and so on. We want to know which method or which procedure is the best. But we have a problem since both x and theta are unknown. X is random, and theta is also unknown. So there's two basic approaches that we can solve this problem. We can take the expectation of the loss function with respect to x, or take the expectation with respect to theta. Let's take the first case, which is the frequentist, or can be seen as the frequentist approach. We take the expectation of x. But what with respect to what probability distribution? Well, we take the same theta that is in the loss function. We consider a bunch of thetas. We take the expectation of x with different theta values, and this way we get rid of the x part. But we still have the theta part here. Since we don't know the true theta, we consider different thetas, and we take the expectation with respect to that theta, different thetas. We get rid of the x part, and we end up with a so-called risk function, which still has the theta part in there. So the risk function is a function of theta. This is now how could we then continue with this approach? We could, or get rid of the theta part. We could then continue by, for example, using the min-max approach, or for example, considering subclasses of delta, for example, the class of unbiased estimators, that we could ultimately then get rid of the theta part. But at this point, this defines as this is the risk function that includes still the theta. Now, the other approach would be to take the expectation of theta. So we can do that. We take the expectation of theta conditioned on x. So this is a conditional expectation. And we can do this, and by doing this we get rid of the theta part. So in this case we consider theta as random. We take the conditional expectation of theta given x, or expectation of the loss function, but theta is considered random here. This is conditional expectation. Then we still have a function of x. We got rid of the theta part, but we still have a function of x. But this is much nicer compared to the frequentist approach, since we have our data. When we collect our actual data, we can plug that in and we will get an actual value here. And then we can actually compare these procedures and get actual values here and make direct comparisons.